patient care areas necessitate a redundant grounding system. This requirement ensures continuous electrical connections and effectively prevents electrical hazards. Type MC cable, characterized as a flexible metal clad cable, is commonly employed for its capacity to offer both grounding and conductor protection. However, general-purpose Type MC cable cannot be utilized in patient care areas that mandate a redundant ground system. Despite this general restriction, certain constructions of MC cable are permissible for use in these specific areas. These include Type MCCU and MCAF cables distinguished by a G suffix. These particular cables are equipped with a green grounding wire in addition to the standard bare grounding conductor. Also acceptable is Type AC cable, which shares similarities with MC cable but includes an additional aluminum armor jacket. The primary reason for the restriction on standard Type MC cable, lacking the G suffix, lies in its failure to provide a redundant grounding path. The inclusion of a green grounding wire in cables with the G suffix or the presence of aluminum armor in AC cables fulfills the necessary redundant grounding requirement. The implementation of redundant grounding systems in patient care areas is critical to maintaining electrical safety and preventing potential hazards. This system involves providing multiple independent grounding paths to ensure that electrical equipment remains safely grounded even if one grounding path fails. The NEC, or National Electrical Code, outlines specific requirements for grounding and bonding in healthcare facilities to minimize the risk of electrical shock and fire. Firstly, the grounding system must be designed to limit the voltage to ground during normal operation and fault conditions. This is achieved by creating a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly clear the fault. Secondly, all metallic equipment and conductive surfaces in patient care areas must be bonded together to create an equipotential plane. This reduces the potential difference between different surfaces, minimizing the risk of electric shock if a patient comes into contact with two different grounded surfaces. Thirdly, the grounding system must be regularly inspected and tested to ensure its integrity. This includes verifying the continuity of grounding conductors, measuring ground impedance, and performing ground fault circuit interrupter, or GFCI, testing. Grounding conductors play a critical role in providing a safe path for fault current to flow back to the source. These conductors must be sized appropriately to handle the maximum fault current that could occur. The NEC provides tables and guidelines for sizing grounding conductors based on the size of the overcurrent protection device. Grounding electrodes, such as ground rods or metal water pipes, are used to connect the grounding system to the earth. These electrodes provide a low impedance path for fault current to dissipate into the ground, helping to limit the voltage to ground during fault conditions. Bonding involves connecting all metallic equipment and conductive surfaces together to create an equipotential plane. This is typically achieved using bonding jumpers and connectors. The goal is to minimize the potential difference between different surfaces, reducing the risk of electric shock. Isolation transformers are often used in critical care areas to provide an isolated power system. These transformers isolate the electrical system from the main power source, reducing the risk of electric shock if a patient comes into contact with a grounded surface. Ground fault circuit interrupters, or GFCIs, are used to protect against ground faults. These devices monitor the current flowing through a circuit and quickly interrupt the power if a ground fault is detected. GFCIs are commonly used in wet locations and patient care areas to provide additional protection against electric shock. Regular inspections and testing are essential to ensure the integrity of the grounding system. This includes visual inspections to check for damaged or corroded conductors, continuity testing to verify the integrity of grounding paths, and ground impedance measurements to assess the effectiveness of the grounding system. The NEC specifies requirements for periodic testing and documentation of grounding systems in healthcare facilities. These requirements help to ensure that the grounding system remains effective over time. In healthcare facilities, maintaining a safe electrical environment is paramount. Redundant grounding systems are a key component of the safety strategy, ensuring that patients and staff are protected from electrical hazards. Only specific types of MC and AC cables that meet the stringent requirements for redundant grounding should be used in patient care areas. These cables provide the necessary grounding paths to minimize the risk of electrical shock and ensure the safe operation of electrical equipment. To summarize, the selection of appropriate cable types for patient care areas is critical for maintaining electrical safety. The use of Type MCCU or MCAL cable with the G suffix, or Type AC cable, ensures that a redundant grounding path is provided, minimizing the risk of electrical hazards. It is essential to adhere to the NEC guidelines and local electrical codes when installing and maintaining electrical systems in healthcare facilities. By doing so, electrical professionals can help to create a safe and reliable electrical environment for patients and staff. Proper grounding and bonding techniques are crucial for preventing electrical shock and fire in healthcare facilities. The use of redundant grounding systems, along with regular inspections and testing, can help to ensure the safety of patients and staff. Staying up to date with the latest codes and standards is essential for electrical professionals working in healthcare facilities. These codes and standards are constantly evolving to address new technologies and emerging safety concerns. Firstly, understanding the specific requirements for grounding and bonding in healthcare facilities. This includes knowing the types of equipment that require grounding, the methods for grounding and bonding, and the testing requirements for grounding systems. Secondly, proper grounding and bonding techniques. This includes using appropriate grounding conductors, making secure connections, and verifying the continuity of grounding paths. Thirdly, using appropriate personal protective equipment, or PPE, when working on electrical systems. This includes wearing insulated gloves, safety glasses, and other protective gear. Fourthly, never working on energized electrical equipment unless absolutely necessary. If it is necessary to work on energized equipment, use appropriate lockout/tagout procedures to prevent accidental energization. Fifthly, inspecting electrical systems regularly for signs of damage or deterioration. This includes checking for loose connections, frayed wires, and corroded equipment. Sixthly, promptly addressing any electrical hazards that are identified. This includes repairing damaged equipment, replacing faulty wiring, and correcting any grounding or bonding deficiencies. Seventhly, documenting all electrical work that is performed. This includes keeping records of inspections, testing, and repairs. Eighthly, seeking guidance from qualified electrical professionals when needed. This includes consulting with electrical engineers, inspectors, and contractors. In healthcare facilities, the electrical system is responsible for powering a wide range of critical equipment, including life support systems, diagnostic equipment, and lighting. A reliable and safe electrical system is essential for ensuring the well-being of patients and staff. Redundant grounding systems play a vital role in achieving this goal by providing multiple independent grounding paths. This helps to minimize the risk of electrical shock and ensure that electrical equipment remains safely grounded even if one grounding path fails. Electrical professionals working in healthcare facilities must be knowledgeable about the specific requirements for grounding and bonding in these environments. They must also be skilled in the proper techniques for installing, maintaining, and testing grounding systems. By following best practices and adhering to the NEC and other applicable codes and standards, electrical professionals can help to create a safe and reliable electrical environment for patients and staff. The use of Type MCCU or MCAL cable with a G suffix, or Type AC cable, is essential for providing a redundant grounding path in patient care areas. These cables provide the necessary grounding conductors and shielding to minimize the risk of electrical shock and ensure the safe operation of electrical equipment. To reiterate, general-purpose Type MC cable should not be used in patient care areas that require a redundant ground system. These cables do not provide the necessary grounding paths to meet the stringent safety requirements for healthcare facilities. The decision to use Type MC cable in patient care areas should be made in consultation with a qualified electrical engineer or inspector. These professionals can assess the specific requirements of the facility and determine the appropriate cable types to use. Regular inspections and testing of grounding systems are essential for ensuring their continued effectiveness. These inspections should be performed by qualified electrical professionals who are familiar with the NEC and other applicable codes and standards. In conclusion, prioritizing patient safety in healthcare facilities necessitates meticulous attention to electrical grounding. The implementation of redundant grounding systems coupled with the utilization of appropriate cable types such as Type MCCU or MCAL cable with a G suffix, or Type AC cable, is paramount in minimizing electrical hazards. Moreover, adhering to established electrical codes and standards, along with regular inspections and testing, contributes significantly to maintaining a safe and reliable electrical environment for both patients and healthcare personnel. Understanding the nuances of grounding systems in patient care areas is not merely a matter of compliance, it is a commitment to ensuring the well-being of individuals who rely on these facilities for their health and safety. The complexities of electrical systems demand a proactive approach, where knowledge and diligence converge to mitigate risks and uphold the highest standards of care. The electrical infrastructure within healthcare settings is an intricate network that supports a multitude of life-saving devices and essential services. From diagnostic imaging to critical care equipment, the seamless operation of these technologies hinges on the integrity of the electrical system. Redundant grounding systems serve as a protective barrier, safeguarding against potential electrical faults that could compromise the functionality of these vital instruments. By providing multiple pathways for electrical current to flow safely to ground, these systems enhance the reliability and stability of the electrical network, reducing the likelihood of disruptions or failures that could jeopardize patient care. Moreover, the importance of selecting the appropriate cable types for patient care areas cannot be overstated. The choice of cable directly impacts the effectiveness of the grounding system and its ability to mitigate electrical hazards. Type MCCU or MCAL cables with a G suffix, as well as Type AC cables, are specifically designed to meet the stringent requirements for redundant grounding in healthcare settings. These cables feature additional grounding conductors and shielding that enhance their ability to provide a safe and reliable electrical connection. By adhering to electrical codes and standards, healthcare facilities can ensure that their electrical systems meet the highest levels of safety and performance. Regular inspections and testing of grounding systems are essential for identifying and addressing potential issues before they escalate into major problems. These inspections should be conducted by qualified electrical professionals who possess the expertise to assess the condition of the grounding system and recommend appropriate corrective actions. The commitment to electrical safety in healthcare facilities is a continuous process that requires ongoing vigilance and investment. By prioritizing the integrity of the electrical system and adhering to best practices, healthcare providers can create a safer and more reliable environment for their patients and staff. The integration of advanced technologies and innovative solutions can further enhance the effectiveness of grounding systems and reduce the risk of electrical hazards. From smart grounding systems that continuously monitor the integrity of the electrical network to wireless sensors that provide real-time data on grounding performance, these advancements offer new opportunities to improve electrical safety in healthcare settings. The pursuit of electrical safety in healthcare facilities is not merely a technical endeavor, it is a moral imperative that reflects a deep commitment to protecting the well-being of patients and healthcare personnel. By embracing a culture of safety and continuously seeking ways to enhance the reliability of electrical systems, healthcare providers can create an environment where patients can receive the care they need without fear of electrical hazards.